Greetings! In this video, we will present our research project Variable Command Response Type Rotorcraft Control System, sponsored by Lockheed Martin Corporation through the Industrial Affiliates Program of the Electrical and Computer Engineering Department. I am Delimar Soto and my teammates are Ángel Roldán, Michael Torres, Daniel Vicens, Kevin Marrero, Nunila Dávila, and Genesis Ayala. Our advisor is Professor Gerson Beauchamp and our company liaison is Wilson Ronda. We are all students of the ECE department of the University of Puerto Rico at Mayagüez.
Helicopters are one of the most versatile and maneuverable aircraft available. Their unique capabilities include vertical takeoff and landing, hovering, and movement towards any direction. For these reasons, they are often used in many critical operations such as search and rescue, surveillance, firefighting, transmission line maintenance, and others. Despite all its capabilities, a helicopter is a very unstable system and is almost impossible to fly without an automatic control system. Flight controllers help to stabilize the helicopter for the pilot. For example, a flight controller could maintain the altitude of the helicopter constant while letting the pilot move forward, backward, and sideways.
This project is focused on the design and implementation of different flight modes for a small-scale helicopter. These flight modes will be implemented in an open-source programmable flight controller called PIXHAWK 2.1. This device has an integrated sensor system for measuring essential flight variables, and it also allows for external sensors to be added. We will determine which control system design method is more adequate to solve our problem. Among these methods, we are studying full-state feedback controllers and robust PID controllers. We are studying these design methods with simpler benchmark problems, like the inverted pendulum, to understand it better. After understanding how it works, we will design and simulate the controllers and their corresponding system responses. After simulating them, the controller will be implemented in the PIXHAWK and the flight responses will be tested in a safe test environment prior to field testing.
This safe test environment will support indoor flight testing for the designed controllers. The safe test environment will be a cage with good airflow constructed around the proving ground. The implementation of this cage will prevent any harm to the operators in case something goes wrong. The helicopter will be anchored to a platform that allows rotation in all axes, roll, pitch, and yaw. That motion will simulate the flight behavior of the helicopter.
Before our last IAP sprint session, our helicopter successfully completed its first and second flights controlled by the Microbeast default controller. The second flight had the purpose of lifting the added weight of the new enclosure. For the third flight, the challenge was to achieve a flight controlled by the PIXHAWK. To make this possible, it was necessary to have the correct wiring, servo directions, channel mapping, and sensor calibration. Before achieving hover, the controller parameters were tuned to reach flight stability. After tuning the controller, the helicopter completed all the pre-flight requirements and completed a stable flight.
To properly integrate a new controller into the PIXHAWK, we must understand the ArduPilot code and find where to add it. For this, we revise and analyze various files in ArduPilot which are all written in C++. ArduPilot supports different flight modes that are similar to the ones we want to design, so we must study how they are implemented to determine the correct approach to add ours. Following guidelines that the ArduPilot support team provides, we downloaded the code and built it to run tests inside the PIXHAWK to make sure the computer and PIXHAWK are communicating effectively.
In the future, we plan to study the closed-loop block diagrams currently implemented in the PIXHAWK by the ArduPilot community. The objective is to use this diagram as a guide to design a full-state feedback controller or controllers of different structures. By developing these new flight commands for the small-scale helicopter, we aim to make the operation of the aircraft accessible for a broader audience. The results achieved and methodologies developed in this project may also be applied to full-scale helicopters.